Good morning, everyone. Hopefully today is a nice Sunday morning for you. What we're going to do today is going to go over the solubility product. Hopefully you'll be able to listen to this today. That way when on Monday we'll go over a few more of these types of free response questions that might show up on the AP test. So let's get started. The first thing we need to study is what KSP is. KSP is the solubility product for equilibrium expressions. We use this to determine how soluble something is. When we are looking at a precipitate, typically, even though it's deemed insoluble, a few molecules of it will actually dissolve or go into solution. So it will form an equilibrium. Even solids that are completely soluble, they'll disassociate, but sometimes because there's so many of the ions disassociated and bouncing around in the solution, that we might have a few ions that bounce back into each other and go back to form that solution. So we write these equations, these precipitate equations, up as equilibrium expressions with a double-headed arrow. So the KSP is the product of the concentration of the ions involved in the equilibrium raised to the power of its coefficients. It's very similar to what we've been doing for the equilibrium expressions for, say, acid-base, or anything else we've been working on. And we'll go over a couple of these in the next slide. The smaller the KSP value means that the compound is less soluble because there's less ions in solution. Okay, so let's have a little bit of practice of writing KSP expressions. But the first thing we wanted to do is if we have AgCl as a solid, and it disassociates a little bit, typically silver chloride, I know it's a solid, but there'll be a tiny bit of silver chlorides that actually will disassociate. Now, most of it will stay together as a molecule, but every now and then there'll be a few of them that will break up. So we would have Ag plus Cl negative. The KSP would just be the product of the concentration of the ions. Now, raised to the power of the coefficient, but in this case there are no coefficients. So the KSP equals the concentration of silver times the concentration of chloride ion. Now for calcium fluoride, now we have, we'll have a coefficient here, because if we write the equilibrium expression, we have calcium 2 plus 2 fluorines with a negative charge. So our equilibrium expression is going to be the concentration of calcium times the concentration of fluorine raised to the coefficient's value, raised to the second power. So KSP is typically determined by laboratory investigations or laboratory experiments, but we can calculate the KSP if the ion concentration is given. Okay, so what we want to do here is we want to, let me fix that typo, there shouldn't be an A there. We are given lead 2 chloride is slightly soluble in water. So we have the reaction of lead 2 chloride breaking down to form lead 2 ions plus 2 chlorine ions in solution. It says to calculate the KSP if the lead concentration has been found to be 1.62 times 10 to the negative 2. So this right here is this value right there. So we can calculate KSP. So let's write the expression. The KSP, the equilibrium expression based on the equation that we have above. So now remember, the lead chloride, lead Roman 2 chloride, that's not going to be in the KSP expression because that's a solid. So we're just going to not put that in there. So we have the concentration of the lead times the concentration of the chlorine ion squared. So, if the lead the concentration of lead is given to us as 1.62, then we can go ahead and figure out what the KSP is going to be. So we know that, I'm going to rewrite this down here. So this is my reaction. Lead to chloride will break down to form Pb 2 plus 2Cl negative. If we know this is X, then we know that chlorine is 2X, because we still have to remember, and we have to make sure that we're dealing with the stoichiometry. So to solve for KSP, I'm just going to write KSP equals, since I already wrote my expression up there, X times 2X squared. And so KSP equals 1.62 times 10 to the negative 2 times 2 times 1.62 times 10 to the negative 2 squared. So if we do our whole calculations, we should get 1.70 times 10 to the negative 5 for the KSP. Okay, so that's how we can use the concentration of the ions to calculate KSP. Now the molar solubility is, basically it's the solubility of the compound, but it's based in terms of molarity. The molar solubility is the number of moles of solute in 1 liter of saturated solution. Now solubility, what we've also been using before, is the number of grams of solute in 1 liter. So the only difference is the molar solubility is based on number of moles, whereas the solubility is just based on number of grams. The molar solubility can be used to calculate KSP. Okay, so we have copper 1 bromide. It has a measured molar solubility of 2.0 times 10 to the negative 4 at 25 degrees Celsius. Calculate the KSP. So the first thing we want to do is we want to write up the equilibrium reaction when copper 1 bromide dissolves. So we have Cu, Br, and that's our solid. And that's going to dissolve into Cu plus Br negative. So if we want to do our rice table, we can, but it's a little bit simpler because this solid right here won't be in the equilibrium expression because it's a solid. So if we're starting off with a certain amount of copper bromide, we know that initially we have no copper ions and no bromine ions, but as the reaction occurs, we will have a certain number of X ions in solution. So they're giving us the molar solubility. So basically what they're doing is the molar solubility, you can think of it in terms of X. So they're giving us X here. So KSP equals the concentration of Cu plus times the concentration of Br negative, and this is going to be X equals X, so KSP equals 2.0 times 10 to the negative 4, and basically you can go ahead and square that. So the KSP equals 4.0 times 10 to the negative 8. Here's another example where we can calculate the KSP from the molar solubility. A couple things I want to correct. This right here should be a subscript 2. The negative 5 right there should be a superscript. So that should be up. Okay, so we have the molar solubility as 1.59 times 10 to the negative 5. Calculate the KSP. So what I want to do is I want to write my reaction first. Iron hydroxide is going to break down to form Fe2 plus 2 OH negative. And this is going to give me X, and this is 2X. So my KSP for this is going to be, KSP is going to equal X times 2X squared, which equals 4X cubed, 1.59 times 10 to the negative 5. And now we're just going to solve for X. Okay, so to solve for X, we could oh, I made a mistake. I need to erase something. Oh no, it's not letting me erase. Well, I need to just cross this out then, because that's not true. So far, KSP equals X times 2X squared. But we're given the molar solubility, so we're given what X is. So now we could just substitute KSP equals 4X cubed. So I'm just going to put X into there. 4 times 1.5 times 10 to the negative 5 cubed. And the correct answer is the KSP equals 1.6 times 10 to the negative 14. So now we're going to do the opposite. We're going to calculate the molar solubility if we are given K. The idea is pretty much the same though. First things first, we're going to write the formula or the equation. So we have Cu okay, so we have the copper iodide, CuIO3 2 is going to break down to form Cu with a 2 plus charge plus 2 iodate ions. So that's my X, that means that's 2X. And this time they're giving us the KSP, so KSP is going to equal the concentration of your copper times the concentration of your iodide ion. And then we got to put that to the second power. So KSP equals X times 2X squared, which equals 4X cubed. And if we have the KSP equals 1.4 times 10 to the negative 7, I want to substitute for X, so I could divide the whole thing by 4 and take the cube root. And we would be doing the same thing on this side. And after we all said and done, after we calculated it, we should get 3.3 times 10 to the negative 3 molar. Okay, common ion. This is a little bit of, we have to go back and think about Le Chatelier's principles a little bit, but what they're saying is the presence of a common ion will cause the equilibrium to shift away from the side of the reaction that has the ion. The solubility of any salt will decrease with the presence of a common ion. So, let's do an example of the common ion. Would magnesium hydroxide be more soluble in an acidic solution or in a base solution? So let's make some corrections on here. This here should be a subscript of 2, and this right here, my arrow should be right there. Le Chatelier's principle says that if a concentration of a reactant or product were added to a reaction, the reaction would shift away from the increase. So if we add more base, and we're talking about like a strong base, so we're going to add more OH ions to the reaction. If we add more OH ions to the reaction, the when we stress that system, the reaction will want to shift this way to relieve that stress, because the shift occurs away from the increase. So if we added more base to this reaction right here with the magnesium hydroxide, we would cause more solid to be formed, or it would be less soluble. And that's another idea of the common ion. Now let's change it up, and let's add an acid to the equation. Now if we add an acid to the equation, since we don't have a common ion, the equation, or the shift, is going to move this way, and we'll have the magnesium hydroxide dissolving or shifting to the right. Okay, so we want to talk about the reaction quotient and KSP. Do you remember Q? We used Q back when we were talking about kinetics. So there it is back. In this case, what we're going to do is we're going to use Q to determine if a precipitate or a solid will form. We can also use it to calculate the concentration of the ions. So a couple things to remember. Do you remember when we would compare KSP and Q? So if we have KSP and we have Q, and if KSP is greater than Q, the system is not at equilibrium. And the solution is unsaturated. Now, if KSP equals Q, then we're at equilibrium, and the solution is saturated. Finally, if KSP is smaller than Q, then again, the system's not at equilibrium. Oops, equilibrium. And the solution is supersaturated. So what we're going to do is we're going to compare Q and KSP to determine if a precipitate will form.